Hello everyone. Today we will study triple integrals in spherical coordinates. Let me first of all introduce what is the spherical coordinate. Let me first of all introduce what's the spherical coordinate system. In the spherical coordinate system, every point P in a three-dimensional space can be represented by an order triple. Rho, theta, phi. They are Greek letters. Rho, theta, phi. They are Greek letters. Rho, theta, phi. So every point P can be represented by an order triple. Rho, theta, phi. Every point P can be represented by order triple. Rho, theta, phi. Next, let me introduce the meaning of rho, theta, and phi. Rho represents the distance from point P to the origin. Let's call the origin O. Rho represents distance from point P to the origin O. So rho represents the distance from point P to the origin O. This is rho. Next, let me introduce theta. For theta, let's find the projection first. Suppose Q is the projection of P in the xy plane. Suppose Q is the projection of P in the xy plane. Theta represents the angle theta represents the angle between the positive x-axis and the segment OQ. Theta between the angle between the positive x-axis and the segment OQ. Theta represents the angle between the positive x-axis and the angle OQ. Theta represents the angle between the positive x-axis and the segment OQ, where Q is the projection of point P where Q is the projection of point P in the xy plane. Q is the projection of P in the xy plane. Theta represents the angle between the positive x-axis and the segment OQ. This angle is angle theta. And keep in mind, this theta is the same theta as in cylindrical coordinate system. Keep in mind that this theta is the same as the theta in the standard cylindrical coordinate system. This theta is the same as the theta in the cylindrical coordinate system. Now, angle phi is different. Angle phi represents the angle between the positive z-axis and the segment OP. Angle phi represents the angle between the positive z-axis and the segment OP. This is angle phi. Angle phi represents angle between the positive z-axis and the segment OP. Next, let me show you the conversion between spherical coordinates and Cartesian coordinates. Let x, y, z be the Cartesian coordinate of point P. And let r theta z be the standard cylindrical coordinate of point P. Then, if r theta z is the standard cylindrical coordinate of point P, r represents distance from point P to z-axis. R represents distance from point P to the z-axis. R represents distance from point P to the z-axis. And when we measure distance, this angle here must be right angle. And this side here is z. This side here is z. R is distance from point P to the positive z-axis. Distance from point P to Q is z. Distance from point P to Q is z. So this side is also z. Distance from P to Q is z. So distance here is also z, since this is a rectangle. So this distance here is z. This is r. So here, rho, r, and z. Rho, r, and z form a right triangle. Rho, r, and z form a right triangle. Now, rho represents distance from point P to the origin. Rho represents distance from point P to the origin. Use Pythagorean theorem whenever rho squared is s squared plus y squared plus z squared. If we use Pythagorean theorem, rho squared is s squared plus y squared plus z squared. Rho is distant from point P to the origin. If you use Pythagorean theorem, it's s squared plus y squared plus z squared. Now, how do we find angle phi? How do we find angle phi? Look at this right triangle here. In this right triangle, this is opposite side, this is adjacent side. This side is opposite, this side is adjacent. Opposite over adjacent is tension. So we know tension phi. Tension phi is R over Z, where R is where R squared is S squared plus Y squared. Tension phi is R over Z, opposite over adjacent, where R is S squared plus Y squared. This R is an R in a cylindrical coordinate system. So R squared equal to S squared plus Y squared. Tension theta. Tension theta. This theta is the theta in spherical coordinate system. Is the theta in cylindrical coordinate system. Tension theta is y over x. Tension theta is y over x. So we use these three formulas to convert from Cartesian coordinates to spherical coordinates. We use these three equations to convert coordinates from Cartesian coordinates to spherical coordinates. That's how we find rho theta phi. No theta phi. That's how we find rho theta phi. Now, backward. If we try to go backward, find SYZ, what can we do? If we try to go backward, find SYZ, what can we do here? Observe this triangle first. Observe this triangle first. This is a right triangle. Z, refer to angle phi. Refer to angle phi. Z is the adjacent side. Rho is the hypotenuse. When we have adjacent and hypotenuse, we can use cosine. We can use function cosine. So, Z in this right triangle, Z equal to rho cosine phi. In this right triangle, Z equal to rho cosine phi. In this right triangle, Z is the adjacent side. Rho is hypotenuse. So Z equal to rho cosine phi. R is the opposite side. Rho is adjacent side. Rho is hypotenuse. R is opposite side. When we have opposite and hypotenuse, we can use function sine. So R equal to rho sine phi. R equal to rho sine phi. Next, in cylindrical coordinate system, x is r cosine theta. In cylindrical coordinate system, x is r cosine theta. I can replace this r with this r here. I can replace this r with this r here. So x actually equal to rho sine phi times cosine theta. S equal to rho sine phi times cosine theta. And similarly, y equal to r sine theta in cylindrical coordinates. Y equal to r sine theta in cylindrical coordinates. And since we can replace r with rho sine phi, I have y equal to rho sine phi sine theta. So x is r cosine theta. I replace r with rho sine phi. So x equal to rho sine phi cosine theta. Y is r sine theta. Y is r sine theta. So I can replace r with rho sine theta. So y can be rewrite as rho sine theta phi sine theta. That's how we convert from spherical coordinate to Cartesian coordinates. That's how we convert from spherical coordinate to Cartesian coordinates. Keep this formula in mind. Keep this formula in mind. That's the relationship between spherical coordinate and Cartesian coordinates. Keep this formula in mind. That's the relationship between spherical coordinates and Cartesian coordinates. Also, in general, In order to make the calculation easier, we usually choose rho to be non-negative. In general, we choose rho to be non-negative between 0 and infinity. We choose rho to be non-negative in order to make the calculation easier. Rho represents distance from point P to origin. We usually make rho to be positive. We choose theta to be between 0 and 2 pi to avoid overlapping. We choose theta between 0 and 2 pi to avoid overlapping. That's one cycle. And how about phi? How about angle phi? For angle phi, let me show you a different picture for angle phi. That's the z-axis. By changing the eye level, we can make SY plane looks like a line. By changing the eye level, we can make SY plane looks like a line. Say point P is here. Theta represents angle between point P and between the line segment OP and the z-axis. This is angle phi. So if P is above SY plane, we see that angle is between, if P is above SY plane, phi is between 0 and pi over 2, between 0 and 90 degrees. If P is above SY plane. If P is below SY plane, suppose P is here, then this is angle phi. If P is below SY plane, then angle phi is between pi over 2 and pi, between 0 and 180. Or if P is here, what's angle phi? Angle phi represents angle between the positive z-axis and the line segment OP. This is angle phi here. So when P is below SY plane, angle phi is between pi over 2 and pi. And when P is above SY plane, angle phi is between 0 and 90 degrees. That means angle phi is always between 0 and pi over 2. Angle phi is always between 0 and pi over 2. Angle phi is always between 0 and pi, between 0 and 180 degrees. It must be at least 0. Angle phi must be at least 0, at most 180. When angle phi located in the positive z-axis, angle phi is 0. When point P is located in the z-axis, angle phi is 0. When point P is located in the negative z-axis, angle phi is 180, which is pi. When point P is located in the SY plane, angle phi is 90 degrees, exactly 90 degrees, which is pi over 2. So angle phi is between 0 and pi. Since angle phi represents angle between the positive z-axis and the line segment OP, angle phi is always between 0 and 2 pi. Keep this in mind. Next, let's look at some examples about conversion between spherical coordinate and Cartesian coordinates. Convert each of the following points from spherical coordinate to Cartesian coordinate. Let me put a formula here. Rho squared is s squared plus y squared plus z squared. Tension theta is y over x. Tension phi is r over z, where r where r squared is x squared plus y squared. That's how we convert from Cartesian coordinate to spherical coordinates. The other way, x is r cosine theta, y is r sine theta, where r is rho sine phi, and z equal to rho cosine phi. That's how we convert from spherical coordinate to Cartesian coordinates. First example, we have a point 3 pi over 3 pi over 6. First point, 3 comma pi over 3 pi over 6. If this point is in spherical coordinates, first number represents rho, second number represents theta, third number represents phi. It must exactly in this order. You must read it exactly in this order. You must read the coordinate exactly in this order. First number represents rho, second number represents theta, third number represents phi. You must read it exactly in this order. Then, based on rho, theta, phi, we try to find s, y, z. So we can find r first. Since both s and y depends on r, we can find r first. R is rho sine phi. R is rho sine phi. So rho here is 3. Angle phi is pi over 6. Sine pi over 6 is half. 3 times half is 3 over 2. This is r. Next, we can find s and y. X is r cosine theta. R is 3 over 2, which we just found. R is 3 over 2. Angle theta is pi over 3. Cosine pi over 3 is also half. 3 over 2 times half is 3 over 4. 3 over 2 times half is 3 over 4. Y is r sine theta. Y is r sine theta. R is 3 over 2. We just found it here. Sine of 3 pi over 2 times sine of 3 pi over 2. Times sine of pi over 3. Sine pi over 3 is radical 3 over 2. Which is 3 radical 3 over 4. That's x, that's y. Next, find z. Z is rho cosine phi. Z is rho cosine phi. Rho is 3 cosine phi. Rho is 3. Angle phi is pi over 6. Cosine pi over 6 is radical 3 over 2. So the answer is 3 radical 3 over 2. So the Cartesian coordinate is 3 over 4, this is x. 3 radical 3 over 4, this is y. 3 radical 3 over 2, this is z. That's the Cartesian coordinates. This is the Cartesian coordinates. This is the Cartesian coordinates. Next. The second point is 2 comma 5 pi over 4. 2 pi over 3. If this is a spherical point, we must read it this way. Rho theta phi. First number represents rho, second number represents theta, third number represents phi. We must read it exactly in this order. So rho is 2. Theta is 5 pi over 4. Phi is 2 pi over 3. We must read it exactly in this order. Next, we try to find S, Y, Z. But we can see that both S and Y depends on R. So we must find R first. Let's find R first. R is rho sine phi. R is rho sine phi. Rho is 2. Angle phi here is 2 pi over 3. Sine 2 pi over 3. This angle 2 pi over 3 located in quadrant 2. Reference angle is pi over 3. Sine pi over 3 is radical 3 over 2. So if we multiply, we get radical 3. This is R. R is radical 3. Next, X is R cosine theta. S is R cosine theta. Here, we just found R. R is radical 3. Angle theta is 5 pi over 4. Cosine 5 pi over 4. 5 pi over 4 located in quadrant 2. Cosine function in quadrant 2 is negative. Reference angle, 5 pi over 4 is in quadrant 3. 5 pi over 4 is more than 180. It's in quadrant 3. Cosine function in quadrant 3 is negative. Reference angle of 5 pi over 4 is pi over 4. Cosine pi over 4 is radical 2 over 2. So S coordinate is negative radical 6 over 2. S coordinate is negative radical 6 over 2. Y coordinate is R sine theta. R is radical 3, which we just found. Theta is 5 pi over 4. Angle theta is 5 pi over 4. Angle 5 pi over 4 located in quadrant 3. Sine function in quadrant 3 is negative. And the reference angle is pi over 4. Sine pi over 4 is radical 2 over 2. If we multiply out, we get negative radical 6 over 2. That's the Y coordinate. For the Z coordinate, use the formula rho cosine phi. Rho cosine phi. Rho is 2. Cosine phi. Angle phi is 2 pi over 3. 2 pi over 3 located in quadrant 2. Cosine function in quadrant 2 is negative. Reference angle of 2 pi over 3 is pi over 3. Cosine pi over 3 is a half. 2 times negative half is negative 1. That's the Z coordinate. Here we can see that when phi is more than 90 degrees, when angle phi is more than 90 degrees, Z coordinate is negative. That means the point is located below SY plane. Z coordinate is negative, means the point located below SY plane. So when angle phi is less than 90 degrees, and point P located above SY plane. When angle phi is more than 90 degrees, angle phi located below SY plane. So Z is negative. So the answer is negative radical 6 over 2, comma, negative radical 6 over 2, comma, negative 1. That's the Cartesian coordinate for this point. Next, convert each of the following points from Cartesian coordinates to spherical coordinates. So first example, 2, -1, radical 5. For Cartesian coordinate, these three numbers represent s, y, z. If we try to convert this point to spherical coordinate, that means we try to find rho theta phi. If we try to convert this point to spherical coordinate, we need to find rho theta phi. So we know x is 2, y is -1, z is radical phi. We try to find rho theta phi. Rho square is always s squared plus y squared plus z squared. So use Pythagorean theorem here. Rho squared equal to s squared plus y squared plus z squared. Plug in. We have 2 squared plus -1 squared plus radical 5 squared. 2 squared is 4. 1 squared, -1 squared is 1. 4 plus 1 is 5. Radical 5 squared is 5. 5 plus 5 is 10. So rho squared is 10. That means rho is radical 10. Rho squared is 10 means rho is radical 10. That's rho. Next, try to find theta. We know tension theta. Tension theta is y over x. Tension theta is y over x. Y over x here is -1 over 2. Y over x is -1 over 2. So reference angle. This is not special. This is not special angle. Reference angle is inverse tan of 1 over 2. This is not special angle. Let's find a reference angle first. Reference angle is inverse tan of 1 over 2. We drop negative sign. Reference angle is always positive. Find reference angle first. Reference angle is inverse tan of 1 over 2. We drop negative sign because reference angle is always positive. Next, based on reference angle, we try to find angle theta. Here, x is positive, y is negative. When x is positive, y is negative. This angle theta located in quadrant 4. Since x is positive, y is negative. Angle theta located in quadrant 4. For angle in quadrant 4, the reference angle is, so for angle in quadrant 4, the angle is 2 pi minus the reference angle. For angle in quadrant 4, the angle is 2 pi minus the reference angle. So this is angle theta. Next, try to find angle phi. Tension phi is R over Z. So we need to find R first. Tension phi is R over Z. Let's find R first. R squared is S squared plus Y squared, which is 2 squared plus -1 squared. That's 5. So R is radical 5. Next, let's try to find angle phi. That's angle phi. Tension phi is R over Z. R is radical phi. R is radical phi. Z is also radical phi. So radical phi over radical phi is 1. So angle phi is inverse tension of 1. And angle phi is inverse tension of 1. And we know tension pi over 4 is 1. So angle phi is pi over 4. Angle phi is pi over 4. So the spherical coordinate here is rho theta phi. That's the spherical coordinate for this point. That's the spherical coordinate of this point. Rho theta phi. Usually we choose theta between 0 and pi over 2. We choose angle phi between 0 and pi. And we pick rho, make rho to be positive. Next point, radical 2, comma, negative radical 2, comma, negative 1, comma, negative 1. If this is a Cartesian point, these three numbers represent s, y, z. If this is a Cartesian point, these three numbers represent s, y, z. So we have x equal to negative radical 2, y equal to negative 1, z equal to negative 1. We need to find rho theta phi. We need to find rho theta phi. Since we are looking for spherical coordinate, we need to find rho theta phi. We know that rho squared is s squared plus y squared plus z squared, which is negative radical 2 squared plus negative 1 squared plus negative 1 squared, which is 2 plus 1 is 4. Since rho squared is 4, rho by itself is 2. Usually we make rho to be positive. Tangent theta is y over x. Tangent theta is y over x, which is negative 1 over negative radical 2, which is 1 over radical 2. Again, this is not special angle. Let's find the reference angle first. Reference angle is inverse tangent of 1 over radical 2. And since this angle, since x is negative, y is negative, since both s and y are negative, tangent theta located in quadrant 3. Since both s and y are negative, tangent theta located in quadrant 3. In quadrant 3, angle theta is pi plus the reference angle. In quadrant 3, angle theta is pi plus the reference angle. So that's angle theta. Next, we try to find angle phi. In order to find angle phi, we must find angle r first. R squared is s squared plus y squared, which is negative radical 2 squared plus negative 1 squared, which is 2 plus 1 equal to 3. R squared equal to 3 means r equal to radical 3. R squared equal to 3 means r equal to radical 3. Next, tangent phi. Tangent phi is r over z. That's radical 3 over negative 1. Radical 3 over negative 1, which is negative radical 3. Angle phi is inverse tangent of negative radical 3. Let's find a reference angle first. Be very careful here, because phi is always between 0 and pi. That means it's either between in quadrant 1, it's either in quadrant 1 or quadrant 2. Reference angle of angle phi is inverse tangent of radical 3. And we know for reference angle itself is always positive, so it drop negative sign. When we are finding reference angle is always positive, so it drop negative sign. And inverse tangent of radical 3, we know tangent to the 60 degree. Tangent 60 degree is radical 3. So the reference angle is pi over 3. Then once we know the reference angle, since tangent is negative, it must be in quadrant 2 here. This phi is either in quadrant 1 or quadrant 2. When tangent of phi is negative, it belongs to quadrant 2. So for angle in quadrant 2, the angle is pi minus the reference angle. Pi minus the reference angle, which is 2 pi over 3. That's angle phi. So the answer is rho theta phi. That's the answer. Rho theta phi. That's a spherical coordinate. Rho theta phi. For reference angles, you need to keep this in mind. Reference angle itself is always positive. Let me review reference angle for you. we'll use it maybe in the future. So let me review reference angle for you. Reference angle is always, for any angle, reference angle is the angle between the terminal side and s-axis. Suppose angle theta is here. This is a reference angle. So in quadrant 1, reference angle is the same as angle itself. Reference angle is the same as angle itself. And angle is the same as reference angle. That's in quadrant 1. They are exactly the same. If angle located in quadrant 2, if an angle located in quadrant 2, this is the reference angle. So in order to find the actual angle theta, we know that reference angle is pi. Reference angle is pi minus theta. If we try to find theta itself, theta is pi minus the reference angle. So that's how we find theta in quadrant 2. Pi minus the reference angle. If an angle located in quadrant 3, if a theta located in quadrant 3 here, reference angle is an angle between the terminal side and the x-axis. This is reference angle here. Pi is here. So reference angle in quadrant 3 is theta minus pi. If we try to find theta based on reference angle, theta is pi. Theta is pi plus the reference angle. That's how we find angle theta in quadrant 3 based on the reference angle. If an angle located in quadrant 4, if angle theta located in quadrant 4, this angle is the reference angle. Reference angle is the angle between the terminal side and the s-axis. So 2 pi is here. So reference angle in quadrant 4 is 2 pi minus angle theta. Reference angle in quadrant 4 is 2 pi minus angle theta. If we try to find theta by itself in quadrant 4, that's 2 pi minus the reference angle. So keep this formula in mind. That's how we use reference angle to find angle itself. That's how we find actual angle based on the reference angle. So when we're doing conversion from Cartesian coordinate to spherical coordinates, we need to use reference angle very, very frequently. We need to find angle using reference angle very frequently. So keep this formula in mind. That's how we find actual angle based on a reference angle. When we're finding theta and phi, we use reference angle very frequently. Next, let's look at some graphs. Draw each of the following graphs, each of the following surface. First one, rho equal to 2. Rho represents distance from a point P to the origin. If the component of theta and phi, are missing here, we consider the set of all points. The set of all points P, where the distance between P and the origin O is 2. The set of all points P where distance between P and origin O is 2. If the distance between a point and origin is fixed, in 2D it's a circle, in 3D it's a sphere. In 2D, it's a circle. In 3D, it's a sphere. So the graph is a sphere. Where distance graph is a sphere. Distance from point P to the origin is 2. That's a sphere of radius 2. That's a sphere of radius 2. This is a sphere of radius 2. This is a sphere of radius 2. The set of all point P, where distance from P to O is 2. Distance from point P to the origin is 2. That's a sphere. Can we verify the answer? Can we verify the answer? In order to verify the answer, we can try to convert this equation to Cartesian equation. Let's convert this spherical equation to Cartesian equation. If I square both sides, we know that rho squared equal to 4. And we know rho squared is s squared plus y squared plus z squared. That's a sphere, center and origin with radius 2. Imagine this graph. That's a sphere, center and origin with radius 2. Imagine this graph. That's a sphere, center and origin with radius 2. Imagine this graph. Next. Phi equal to 3 pi over 4. Phi equal to 3 pi over 4. What kind of graph it is? Here, rho is missing. Theta is missing. What kind of graph it is? Angle phi represents angle between the positive z-axis and the line segment OP is 3 pi over 4. So that represents the set of all points P where the distance between where the angle between the positive z-axis and the line segment OP is 3 pi over 4. Angle between the positive z-axis and the line segment OP is 4. Let's draw the picture. Let me draw the picture this way. If we change eye level, we can make SY plane looks like a line. If we change the eye level, we can make SY plane looks like a line. And this is the z-axis. We are looking for the set of all points P, where the angle between the positive z-axis and line segment OP is 3 pi over 4. O is here. 3 pi over 4 is more than 90 degrees, so it goes below SY plane. And we can measure the angle in the other direction. Basically, start from z-axis, there are infinitely many directions. From z-axis, if we try to go down, move down, there are infinitely many directions. So it looks like a cone. If from a cone, point P could be here, could be anywhere. Point P could be anywhere here. It's a cone. This is a cone open downward. This is a cone open downward. Can we verify the answer? Can we verify the answer? Let's try to change this equation to Cartesian equations. Let's try to change this spherical equation to Cartesian equation. Theta is 3 pi over 4. If we apply tension to both sides, So here, angle phi is 3 pi over 4. If we apply tension to both sides, tension phi is tension of 3 pi over 4. Tension phi is R over Z. Tension phi is R over Z. Tension phi is R over Z. Tension of 3 pi over 4. 3 pi over 4. 3 pi over 4 located in where? 3 pi over 4 located in quadrant 2. 3 pi over 4 located in quadrant 2. For reference angle in quadrant 2, take pi minus the angle itself. Take pi minus the angle itself. We can find a reference angle. Pi minus 3 pi over 4 is pi over 4. We have tension pi over 4. Tension pi over 4 is 1. And tension in quadrant 2 is negative. So R over Z is negative 1. If I multiply both sides by negative 1, if I multiply both sides by negative Z, Z equal to negative R. If I multiply both sides by negative Z, Z equal to negative R. Then if I square both sides, Z squared equal to R squared. And we know that R squared is S squared plus Y squared. R squared is S squared plus R squared is S squared plus Y squared. This is a cone. This graph is a cone. This graph is a cone. It's a circular cone. This graph is a circular cone. This graph is a circular cone. But since Z is always negative, since Z is negative R, since Z is negative, it's a cone open downward. Since Z is negative, we don't have an upper half. Since Z is negative, we don't have upper half. We only have the lower half cone. Which match this graph here. Let's match this graph here. Next, rho equal to 4 cosine phi. Now it's hard to tell what kind of graph it is. Now it's very hard to tell what kind of graph it is. It's very hard to tell here. So here we try to first of all change this equation to Cartesian equation first. Change the coordinate to Cartesian coordinates. If we can't tell the graph directly, try to change the equation to Cartesian equation first. So let's try. If I multiply both sides by rho, I can make rho squared equal to 4 rho cosine phi. If I multiply both sides by rho, I can make 4 rho cosine phi. And we know that rho squared is S squared plus Y squared plus Z squared. Rho squared is S squared plus Y squared plus Z squared. Number 4 stays the same. How about rho times cosine phi? How about rho times cosine phi? Rho times cosine phi is Z. So here I can move everything over. S squared plus Y squared plus Z squared minus 4Z. Then I can try to complete square. I can try to complete square for Z squared minus 4Z. If I add 4 to both sides, S squared plus Y squared plus Z squared minus 4Z plus 4 equal to 4. Then this equation can be rewritten as S squared plus Y squared plus Z minus 2 squared equal to 2 squared. That's a sphere. Center at 0, 0, 0, 2 with radius 2. It's a sphere. center at 0, 0, 2 with radius 2. Zero, 0, 2 somewhere here, 0, 0, 2. Radius 2. So distance from the point, distance from this point to the origin is also 2. So this point, this graph, this sphere tensions the origin. This sphere tension to the origin. It's a ball sits above. It's a ball of radius 2 sits above the SY plane, center and origin. Next, rho equal to 2 secant phi. Rho equal to 2 secant phi. If we look at the equation, it's very hard to tell what kind of graph it is. So let's try to convert to Cartesian equation first. Secant can be rewritten as secant phi can be rewritten as 1 over cosine phi. So rho equal to, I can write rho equal to 2 over cosine phi. Secant can be rewritten as 1 over cosine. So rho can be rewritten as 2 over cosine phi. If I multiply both sides by cosine phi, we have rho cosine phi equal to 2. And rho times cosine phi is z. Equation z equal to 2 is a plane parallel to the SY plane and passing through 2 in the z-axis. This is a plane parallel to the SY plane and passing through 2 in the z-axis. So that's a plane parallel to the SY plane, passing through 2 in the z-axis. Next, rho equal to 3 cosecant phi. What kind of graph it is? It's hard to tell directly. So we can first of all rewrite cosecant as 1 over sine. Rho can be rewritten as 3 over sine phi. Rho can be rewritten as 3 over sine phi. And then I can multiply both sides by sine phi. We have rho sine phi equal to 3. We have rho sine phi equal to 3. And we know rho times sine phi is r. Next, I can square both sides. I have r squared equal to 3 squared. R squared can be rewritten as s squared plus y squared. And we know that r squared can be rewritten as s squared plus y squared. And in 2D, that's a circle. In 3D, it's a cylinder. In 3D, it's a cylinder. Center at the z-axis with radius 3. In 3D, this is a cylinder. Center at the z-axis with radius 3. That's the cylinder. Center and origin. Center and z-axis with radius 3. Next, rho equal to 2 cosine theta. Sine phi. Rho equal to 2 cosine theta sine phi. Again, this formula is not simple. We try to convert to Cartesian equation first. This equation is not simple. Let's try to convert to Cartesian equation first. If I multiply both sides by rho, I can make rho square equal to 2 times rho. I bring sine phi to the front. Sine phi cosine theta. I bring sine phi to the front. So rho square equal to 2 rho sine phi cosine theta. Rho square is s square plus y square plus z square. Rho times sine phi. Rho times sine phi is r. Rho times sine phi is r. Cosine theta stays the same. And we know r cosine theta is x. R cosine theta is x. Next, I can bring s over and complete squares. I have s squared minus 2x plus y squared plus z squared equal to 0. If I complete square, I can add 1 to both sides. S squared minus 2x plus 1 plus y squared plus z squared equal to 1. So I have x minus 1 squared plus y squared plus z squared equal to 1. That's a circle center at 1, 0, 0 with radius 1. That's a circle center at 1, 0, 0 with radius 1. Let's draw the sphere first. That's a sphere centered at the point 1, 0, 0 and with radius 1. That's this graph. Next example. Draw a solid that satisfies all given conditions. Draw a solid that satisfies all given conditions. First one, rho is between 0 and 2. Theta is between 0 and 2 pi. phi is between 0 and pi over 3. So rho represents radius from 0 to 2. Theta is the angle start from positive x-axis, which is from 0 to 2 pi, which means a full cycle, above xy plane. And phi is from 0 to pi over 3. That means the angle from positive z-axis is pi over 3. So the solid looks like this. Rho is from 0 to 2, so radius is 2. And theta is from 0 to 2 pi, means it's a full cycle around z-axis. It's a full cycle around z-axis. And rho is from 0 to pi over 3. 0 to pi over 3 rho is 2. It looks like ice cream cone. The graph looks like ice cream cone. The graph looks like ice cream cone. Rho is from 0 to 2. This distance is 2. Rho is from 0 to 2. Theta is from 0 to 2 pi, means around z-axis. We have a full cycle around z-axis. Phi is from 0 to pi over 3. This angle is pi over 3. This angle is pi over 3. So it looks like ice cream cone. The graph looks like ice cream cone. This solid is an ice cream cone. Next example. Rho is between 2 and 3. Theta is between 0 and pi over 2. Means in the xy plane. Theta between 0 and pi over 2 means in the xy plane. We only draw in the first quadrant in the xy plane. Phi is from 0 to pi over 2. Means we only draw everything above xy plane. Phi is between 0 to pi over 2 means we only draw everything above xy plane. And since theta is between 0 and pi over 2, that's in the first quadrant in the xy plane. And since the graph is also above xy plane, z must be positive. This means the graph in the first octane. And rho is between 2 and 3, means radius is between 2 and 3. So theta between 0 and pi over 2. This angle is from 0 to pi over 2. 0 to pi over 2. Phi is between 0 to pi over 2. 0 to pi over 2. 90 degrees. Rho is from 2 to 3. 3 is here. 2 is here. Rho is from 2 to 3. So the solid is everything outside the inner circle, but inside the outer circle. It's everything between these two spheres. The solid is everything between these two spheres. The solid is everything between these two spheres in the first octane. The solid is everything between these two spheres in the first octane. That's the inner sphere. Inner sphere radius is 2. Outer spheres radius is 3. The solid is everything between these two spheres in the first octane. Next, let me introduce triple integrals in spherical coordinates. First of all, for triple integrals of function f over a solid region, we first of all treat function f as a density function over the solid region. Then the triple integral represents the total mass of the solid. The triple integral represents the total mass of the solid region, in the solid region. So we first of all let f of rho theta phi be a positive function. Since in general density is positive, let f of rho theta phi be a positive function. Let B be the point of rho theta phi. Let B be the set of points rho theta phi in R3, where rho is between A and B. Rho is between A and B. Usually rho must be greater than 0. Rho must be non-negative. Theta is between alpha and beta. Usually we treat theta is between alpha and beta. Usually you consider alpha and beta in the first cycle between 0 and 2 pi. Theta between alpha and beta, which is between 0 and 2 pi in the first cycle. And phi is between gamma and delta. Angle phi is between gamma and delta, which is between 0 and pi. Angle phi is between gamma and delta, between 0 and pi. This is called a spherical box. This is called a spherical box. This is called spherical box. Let me show you the picture. The picture looks like this. Suppose that's the spherical box B. Suppose this is the spherical box B, where rho is from A to B. Rho is from A to B. Theta is from alpha to beta. Theta must be measured in the SY plane. Theta must be measured in the SY plane. Theta must be measured in the SY plane, or on a plane that parallel to the SY plane. Angle theta must be measured in the SY plane, or the plane that parallel to the SY plane. So here I measure angle theta in the SY plane. Theta must be between alpha and beta. And angle phi must be between gamma and delta. Angle phi must be between gamma and delta. So on this plane here, phi is gamma. On this plane here, phi is delta. So angle phi is between gamma and delta. This is the spherical box B. This is the spherical box B. Next. Suppose f of rho theta phi is continuous. Suppose f of rho theta phi is continuous on the spherical box B, and we treat f of rho theta phi, we treat this function as the density function. We treat this function f as the density function over the solid region B. We treat f of rho theta phi as the density function over B. We try to evaluate triple integral f of rho theta phi over the solid region B by finding the total mass of B. In order to find the total mass of the spherical box B, I will first of all divide the spherical box B into small boxes, then find the mass of each boxes, then add them up with the mass of the total spherical box. So let's first of all divide the interval rho from A to B into n subintervals. So A will be rho sub 0, rho sub 1, rho sub 2. In general, a typical one in the middle will be rho sub I minus 1, rho sub I. The second last one will be rho sub m minus 1, and B will be rho sub n. And also, I divide interval of angle theta divided interval of an angle from alpha to beta into m subintervals. Alpha will be theta sub 0. Beta will be theta sub m. A typical one in the middle. We have theta 1, theta 2, theta 3. A typical one in the middle will be theta j minus 1 and theta j. That's a typical interval in the middle. And for angle theta, do the same thing. For angle phi, do the same thing. Angle phi from gamma to delta. We divide angle phi from gamma to delta into L subintervals. So gamma will be phi sub 0. Gamma will be phi sub L. Divide this interval into L subintervals. Delta will be phi sub L. Delta will be phi sub L. So divide this into m subintervals. A typical one in the middle. A typical one in the middle will be phi sub k minus 1 and phi sub k. Then a typical box in the middle. A typical box in the middle looks like this. This will be a typical box in the middle. Then in this box, that's a typical box in the middle. That's a typical box. Row sub I minus 1, row sub I is here. Theta j minus 1 and theta j is an angle here. Theta j minus 1, theta j. And phi k sub minus 1, phi sub k. This is a typical box in the middle. Then we pick sample point. We pick sample point to approximate the density of the box. We pick sample point in the middle to approximate the density of the box. We call the sample point here rho sub I star, theta sub j star, and phi sub k star. That's a sample point. We'll use this point to approximate the mass of the box. We use this point to approximate the density of the box. Then the mass of this box will be density times the volume. So density will be F of rho sub I star, theta sub j star, and phi sub k star. That's the density of the typical box. Volume of the box is delta Vijk. Volume of the box is delta Vijk. Density times volume is the mass of this typical box. Density times volume is the mass of this typical box. Then, if we find the sum of all boxes, take sum that k goes from 1 to L. J goes from 1 to M. I goes from 1 to N. if I find all the sums, if I find the sum, k goes from 1 to L, theta goes from 1 to m, I goes from 1 to n, then I find the total mass of this entire spherical box. But this is approximate. This is approximate. This is approximate mass. This is an approximate mass. In order to find the actual mass, we must take a limit. So take a limit as the maximum of delta rho I goes to 0. Maximum of theta j goes to 0. Maximum of delta phi sub k goes to 0. If I take a limit here, this is delta rho I. This is delta rho I. This angle here is delta theta j. That's delta phi sub k. If I take limit as the maximum delta rho sub I, if I take limit here as maximum delta rho sub I and maximum delta theta sub j and maximum delta phi sub k goes to 0, this box will be very, very small. This box will be very, very small. Then if I add them up, it will be the actual sum. It will be the actual sum of the total mass of the spherical box. So this is the triple integral f of rho theta 5 dv. This is triple integral f of rho theta 5 dv over the spherical box B. Next, we try to compute delta, the volume of this spherical box, the volume of each boxes, the delta Vijk. We try to compute the volume of this box. How do we compute the volume of delta Vijk? How do we compute the volume of this typical box? How do we find the volume of this typical box? Let's zoom in. Let's zoom in to see the dimension. Let's zoom in to see the dimension. If I zoom in, this typical box will look like this. If I zoom in, this typical box will look similar as this spherical box. If I zoom in, if I zoom in, this will be rho theta, rho sub I minus 1. This is rho sub I here. This angle will be theta sub j minus 1. This angle here will be theta sub j. This plane here will be the angle phi equal this angle phi sub k minus 1. And for this plane here, the angle will be phi sub k. Next, we try to find the volume of this box. If we cut it very, very small, if we cut this box very, very small, it will be very, very close to a rectangular box. If we cut it very, very small, if we cut it into very, very small pieces, this box will be very, very close to the rectangular box. Then we can try to find the volume of the rectangular box. Then we can try to find the volume of the rectangular box. For the rectangular box, the volume is length times width times height. The volume is length times width times height. Can we tell what's the length, what's the width, what's the height? The length will be this side. The width is easier. The width is delta rho I. The width is easier, delta rho I. The width is easier, delta rho I. In order to find the length and the height, I will use the sample point. I will use the sample point to find the length and the height. Suppose the sample point is here. Sample point is rho I star theta j star phi sub k star we can use this side to approximate the height, the length. I can use this side to approximate the length, and use this side, use this arc to approximate the height. I will use this arc to approximate the length, this arc to approximate the height. For this arc here, central angle is delta phi sub k. Central angle is delta phi sub k. Radius will be rho sub I star. So for this arc, radius will be rho I star. Central angle will be delta phi sub k. For this arc here, radius will be rho sub I star. And the central angle is delta phi sub k. For the length, we can use this arc to approximate the length. We can use this arc to approximate the length, to approximate this side, the length of the rectangular box. So for this arc here, the angle is delta theta sub j. Since delta theta j is a projection of an angle in the xy plane, we cannot use rho as a radius. We must use r as a radius. So we must use the sample point r ijk as the radius times the central angle delta theta j. We cannot use rho because theta is an angle. It's a projection of an angle in the xy plane. We cannot use rho as a radius. We must use r as a radius. And we know that in general, r is rho sine phi. In general, r is rho sine phi. Since we are using the sample point here, rho will be rho sub I star. Phi will be phi sub k star. R will be r sub r. Since r is also a sample point, r depends on the sample point. So we write R sub ijk star equal to rho sub I star sine of phi sub k star. So we have rho sub I star times sine of phi sub k star times delta theta j. Now if we multiply out for the volume, we take length times width times height. For the volume, take length times width times height. So delta Vijk, delta Vijk will be length times width times height, which is multiply out we have rho sub I star twice, rho sub I star square, we have rho sub I star twice, sine of phi sub k star times delta rho I delta theta j times delta phi sub k. That's the volume of each boxes. So the volume of each boxes is rho sub I star square times sine of phi sub k star times delta rho sub I times delta theta sub j times delta phi sub k. So this, if I plug in, this formula can be rewritten as triple integral f of rho theta phi dv over b is the limit maximum delta rho sub I goes to 0. Maximum delta theta sub j goes to 0. Maximum delta phi sub k goes to 0. Sigma I from 1 to n, j from 1 to m, k from 1 to l, f of rho sub I star, theta sub j star, phi sub k star times rho sub I star twice, rho sub I star square sine of phi sub k star times delta rho I delta theta j delta phi sub k. Next, if I let g sub rho theta phi equal to f of rho theta phi times rho square sine phi, then g of rho sub I star theta sub j star phi sub k star can be rewritten as f of rho sub I star theta sub j star phi sub k star times rho sub I star square. We substitute rho sub I star for each row. Rho sub I star square times sine of phi sub k star, because we plug in rho sub k star for rho. Sorry, we plug in phi sub k star for phi. That's what we have here. So if I plug in g for f, this integral can be rewritten as, so this triple integral can be rewritten as limit as the maximum delta rho sub I goes to 0. Maximum delta theta sub j goes to 0. Maximum delta phi sub k goes to 0. I substitute g for f. Substitute g for f of f times rho sub I star square sines of phi sub k star. Substitute g for this. I have g of rho sub I star phi theta sub j star phi sub k star times delta rho I, delta theta j, delta phi sub k. Then by Fubini's theorem, this limit can be rewritten as phi is from gamma to delta. Let's do theta first. Theta is from alpha to beta. Theta is from alpha to beta. Phi is from gamma to delta. Phi is from gamma to delta. And rho is from A to B. In this spherical box, theta is from alpha to beta, phi is from gamma to delta, rho is from A to B. We have function g of rho theta phi, d rho, d phi, d theta. It must match this order: d rho, d phi, d theta. D rho, d phi, d theta. If I replace g with function f, I have the integral theta from alpha to beta, rho from gamma to delta. Phi from gamma to delta, rho from A to B. F of rho theta phi rho square sine phi d rho d phi d theta. This is the triple integral in spherical coordinate. This is the triple integral in spherical coordinate. This is the triple integral in spherical coordinate. This is the triple integral in spherical coordinates. Now, next, what if f is a function of syz, what should we do? If f is a function of syz, what should we do? If f is a function of syz, we can write SYZ in terms of rho theta phi. If f is a function of SYZ, I can write SYZ in terms of rho theta phi. So write SYZ in terms of rho theta phi. Keep in mind that Z is always rho cosine phi. X is r sine theta. X is r cosine theta. Y is r sine theta, where r, for both cases, r is rho sine phi. So plug in. X is rho sine phi times cosine theta. Y is rho sine phi times sine theta. Z is rho cosine phi. Write SYZ in terms of rho theta phi. Write SYZ in terms of rho theta phi. Now we know that this is a function. This is a function of rho theta phi. This is a function of rho theta phi. This is a function of rho theta y. This is a function of rho theta phi. So by this formula, it can be rewritten as integral theta from alpha to beta, phi from gamma to delta, rho from A to B, f of rho sine phi cosine theta, rho sine theta, rho sine phi sine theta, rho cosine phi. Keep it in mind, dv for spherical coordinate, dv is rho square sine phi, d rho, d phi, d theta. Keep in mind, dv is always rho square sine phi, d rho, d phi, d theta. For triple integral in spherical coordinate, dv is always rho square sine phi, d rho, d phi, d theta. Then plug in here, dv is rho square sine phi, d rho, d phi, d theta. This is how we change. That's how we change from Cartesian coordinate to spherical coordinate in a triple integral. So let me write everything over. Change from Cartesian to spherical coordinates. In a triple integral. Let me know everything in detail here. Let B be a spherical box. Let B be a spherical box, so B can be written as a point of rho theta phi in R3. B is the set of all points rho theta phi in R3, where rho must be positive. So rho is between A and B. It must be greater or equal to 0. Rho cannot be negative. theta must be between 0 and 2 pi. Theta is between alpha and beta, and theta must be between 0 and 2 pi. Between 0 and 2 pi. Phi must be between 0 and pi. Phi is between gamma and delta. Phi is between gamma and delta. Phi must be between 0 and pi. So let B be a spherical box. Suppose F is continuous on B. Suppose F is continuous on B. Then the triple integral f of syz over b. The triple integral f of syz over b can be written as theta from alpha to beta, phi from gamma to delta, phi from gamma to delta, rho from A to B. F of rho sine phi cosine theta. F of rho sine phi sine theta. Rho cosine theta times rho square times rho square sine phi d rho d phi d theta. This is how we change from Cartesian coordinate to spherical coordinates. That's how we change from Cartesian coordinate to spherical coordinates. Keep this formula in mind. And the main thing is keep in mind that for spherical coordinate, dv is rho square sine phi d rho d theta, d rho d phi d theta. That's also important. Keep it in mind. For spherical coordinate, dv is always rho square sine phi d rho d phi d theta. And that's how we change from Cartesian to spherical coordinates. More generally, we can also change coordinates for triple integral over some other solid, not only spherical box. Then the solid region E. Then the solid region E be defined as E is the set of points rho theta phi in R3, where theta is between alpha and beta, which is between 0 and 2 pi. Phi is between gamma and delta, which is between 0 and pi. And if rho is between two surfaces, say G1 of theta phi and G2 of theta phi, we can also change coordinates for triple integral over the solid region E. If rho is between two surfaces, G sub 1 of rho theta phi, G sub 2 of rho theta phi. That's the inner surface. That's the outer surface. That's the surface closer to the origin. G1 must be passive. Rho must be passive. So this surface is closer to the origin. This surface is further away from the origin. When rho is between two surfaces, when the solid region E is bounded by two surfaces, this surface is closer to the origin. This surface is further away from the origin. We can also change coordinates for triple integral over this type of solid region. Here, rho is between two surfaces. This surface is closer to the origin. This surface is further away from the origin. If f is continuous, on E, then the triple integral over the solid region E can be rewritten as theta from alpha to beta, phi from gamma to delta, rho from the closer one to the closer surface to the further surface, from the surface closer to the origin to the surface further away from the origin. The surface may be written in terms of theta and phi. The surface may be written in terms of theta and phi. In general, f is a function of s, y, z. We change s, y, z. We write x, y, z in terms of rho, phi, and theta. We write s, y, z in terms of rho, theta, and phi. We write s, y, z in terms of rho, theta, and phi. X is rho sine phi cosine theta. Y is rho sine phi sine theta. Z is rho cosine phi. And dv is always rho square sine phi d rho d theta d rho d phi d theta. That's how we change coordinates for some general solid. That's how we change coordinates for triple integral over some general solid. It's very similar as change coordinates over a spherical box. It's very similar. The only difference is rho may be bounded. The solid may be bounded by two surfaces. That's the closer one, and that's the further away. That's the surface closer to the origin. That's the surface further away from the origin. Next, let's look at some examples. First one, evaluate the triple integral of z over the solid region E, where E is the set of points rho, theta, phi belong to R3, where such that theta is between 0 and pi, phi is between 0 and pi over 2, rho is between 0 and 2 sine phi, rho is between 0 and 2 sine phi. So let's set out the integral first. Theta is between 0 and pi. Phi is between 0 and pi over 2. Rho is between 0 and 2 sine phi. We need to write the function of s, y, z in terms of rho, sine, and phi. Here we know that z is rho cosine phi. Z is rho cosine phi. And dv is rho square sine phi d rho d phi d theta. Keep in mind that for triple integral in spherical coordinate, dv is always rho square sine phi d rho d phi d theta. Keep this formula in mind. Then we try to evaluate integral here. Let's simplify the integrand first. Theta is from 0 to pi. Phi is from 0 to pi over 2. Rho is from 0 to 2 sine phi. Rho times rho square is rho cube. We have cosine phi times sine phi. D rho, d phi, d theta. So we solve the inner integral first. Take antiderivative with respect to rho. Take antiderivative with respect to rho. Take antiderivative with respect to rho. We have rho to the power 4 over 4. Cosine phi, sine phi. Rho is from 0 to 2 sine phi. D phi, d theta. Then substitute upper and lower limit. If I substitute lower limit, I get 0. So all we need is substitute upper limit. If we substitute upper limit, 2 to the power 4 is 16. 16 times 1 over 4 is 4. Sine to the power 4. Sine to the power 4 of phi. Sine phi to the power of 4 times another sine phi. That's sine raised to power of phi. Cosine phi. D phi, d theta. And here, the integrand can be written as a function of phi times function of theta. And limits are constants, so I can separate this into two integrals. Theta is from 0 to pi. Integrand for theta is 1. Phi is from 0 to pi over 2. Integrand is 4 sine phi, 4 sine to the power of phi, cosine phi, d phi. The first one is simple. Take antiderivative for 1. We have theta evaluate from 0 to pi, which is pi. That's the first integral. Second integral, we use U substitution. Second integral, here we use U substitution. Let U be sine phi. Du will be cosine phi, d phi. Then substitute. We have integral 4u to the power 5 times du. If we plug in pi over 2 to phi here, sine pi over 2 is 1. If we substitute 0 for phi here, sine 0 is 0. Take antiderivative. We have 4u to the power 6 over 6. Evaluate from 0 to 1. If we substitute 0, we get 0. If we substitute 1, we get 4 over 6, which is 2/3. That's the second integral. Then we multiply the answer. Pi times 2/3. The final answer is 2 pi over 3. The final answer is 2 pi over 3. If we multiply the answer from each integral, final answer is 2 pi over 3. Next example. Evaluate the triple integrals of xy over the third region E, where E is the set of rho theta phi in R3, such that theta is between 0 and pi over 2, phi is between 0 and pi, and rho is between 0 and 1 minus cosine phi over 2. Let's first of all set up the triple integral using spherical coordinates. So triple integral of sy over third region E dv, that can be written as outer integral theta is from 0 and pi over 2. Theta is between 0 and pi over 2. Angle phi is between 0 and pi. Rho is between 0 and 1 minus cosine phi over 2. Next, we try to write x and y in terms of rho, theta, and phi in spherical coordinates. Try to write x and y in terms of rho, theta, and phi. We know that in spherical coordinates, x is always rho sine phi, cosine theta. Y is always rho sine phi, sine theta. So plugging x and y. Plugging x and y here. X is rho sine phi, cosine theta. Y is rho sine phi, sine theta. How about dv? In spherical coordinates, dv is always rho square sine phi, d rho, d phi, d theta. So dv is rho square sine phi, d rho, d phi, d theta. Next, let's simplify the integrand. Theta is from 0 to pi over 2. Phi is from 0 to pi. Rho is from 0 to 1 minus cosine phi over 2. Simplify the integrand. Rho times rho square is rho raised to power 4. Sine phi times another sine phi is sine cube of phi. And cosine theta times sine theta is cosine theta sine theta, d rho, d phi, d theta. Next, we take the inner integral first. So for the inner integral, take antiderivative with respect to rho. Keep outer integral the same. Take antiderivative with respect to rho. I get rho to the power phi times 1 over phi. Sine cube phi stays the same. Cosine theta, sine theta stays the same. Evaluate rho from 0 to 1 minus cosine phi over 2. d phi, d theta. Then plug in the upper and lower limit, take difference. We know that the lower limit is 0. When I plug in 0 for rho, I get 0. So it disappears. All we need is plug in the upper limit for rho. If I plug in the upper limit for rho, I get 1/5 times 1 minus cosine phi raised to power phi over 2 to the power phi. 2 to the power phi is 32. Sine cube of phi. Cosine theta, sine theta, d phi, d theta. Next, let me rewrite the integral. It can be rewritten as theta from 0 to pi over 2, phi from 0 to pi, 1 over 160 times 1 minus cosine phi raised to power phi, sine cube of phi, cosine theta, sine theta, d phi, d theta. Since the integrand can be written as a product of function of phi and function of theta, and the limits are constants, I can split this double integral into 2 single integrals. So theta is from 0 to pi over 2. Cosine theta, sine theta, d theta. Phi is from 0 to pi. Function of phi is 1 over 60 times 1 minus cosine phi to the power phi times sine cube of phi d phi. Then we can solve each integral individually and multiply their answer together. Let me solve for the first integral first. For the first integral, I can make u substitution. Let u be sine theta. Then du will be cosine theta, d theta. Then this integral can be rewritten as u du. Sine theta is u, cosine theta d theta is du. And for the upper and lower limit, if I plug in pi over 2, sine pi over 2 is 1. If I plug in 0, sine 0 is 0. So I'm going to integral from 0 to 1, u du. Take antiderivative, I get u squared over 2 from 0 to 1. If I plug in 1, I get half. If I plug in 0, I get 0. So the answer for the first integral is half. Next, let's solve the second integral. Let me solve it here. Second integral is from 0 to pi. 1 over 160, 1 minus cosine phi raised to power phi. Sine cube phi d phi. I can first of all pull out 160. Leave 1 minus cosine phi to the power phi the same. Sine cube phi can be rewritten as sine squared phi times sine phi. Then sine squared phi can be rewritten as 1 minus cosine squared phi. And use the formula for difference of perfect squares. 1 minus cosine phi can be rewritten as 1 minus cosine phi times 1 plus cosine phi. So this integral can be rewritten as 1 over 160 integral from 0 to pi 1 minus cosine phi raised to power 6. 1 minus cosine phi to the power phi times 1 minus cosine phi is 1 minus cosine phi to the power 6 times 1 plus cosine phi. And sine phi stays the same. Sine phi d phi. Next, we make u substitution. The u be 1 minus cosine phi. The u be 1 minus cosine phi. Then du will be sine phi d phi. Plug in, I get 1 over 160 u to the power 6. How about this? How about 1 minus sine phi? How about 1 minus cosine phi? From this equation, if I solve this equation for cosine phi equal to 1 minus u. And if I add 1 to both sides, 1 plus cosine phi will be 2 minus u. So 1 plus cosine phi can be rewritten as 2 minus u. And sine phi d phi is du. For the upper and lower limit, I plug in 0 and pi into this function here, find u. If I plug in pi for phi, cosine pi is negative 1. 1 minus negative 1 is 2. If I plug in 0, cosine 0 is 1. 1 minus 1 is 0. So that's a new limit from 0 to 2. Next, I can distribute u to the power 6 into the parentheses. I get 2u to the power 6 minus u to the power of 7 du. Then take antiderivative. I get 2 over 7 u to the power 7 minus 1 over a u to the power of a. Evaluate from 0 to 2. If I plug in 2 to the power 7 is 128. 128 times 2 over 7 is 256 over 7. If I plug in 2 for u, 2 to the power a is 256. 1 over a times 256 is 32. If I plug in 0, I get 0. Then in the parentheses, 256 over 7 minus 32 is, use my calculator, I get 32 over 7. Then take 1 over 160 times 32 over 7, use my calculator, I get 1 over 35. So here, the answer for the first integral is 1 over 2. Answer to the second integral is 1 over 35. So for the final answer, we multiply the answer for both integrals together. I get 1 over 2 times 1 over 35. That's an answer to the first integral, and that's an answer to the second integral. For the final answer, multiply together, 1 over 2 times 1 over 35 is 1 over 70. Next example, evaluate the triple integral x squared plus y squared plus z squared over the solid region E, where E is a region between two spheres, x squared plus y squared plus z squared equal to 4, and x squared plus y squared plus z squared equal to 4 equal to 16. Let's draw solid region E first. E is the region between two spheres. E is the region between two spheres. E is a region between two spheres. E is a region between two spheres. So, if we set out the integral, radius is from 2 to 4. For the first sphere, radius is 2. For the second sphere, radius is 4. So rho is from 2 to 4. For the first sphere, radius is 2. For the second sphere, radius is 4. So rho is from 2 to 4. This is a full cycle. This is a full cycle. This graph, this solid is a full cycle around z-axis. This solid is a full cycle around z-axis. So theta is from 0 to 2 pi. And this solid including region above xy plane and below xy plane. So phi is from 0 to pi. This solid including region around above xy plane and below xy plane. So the angle is 0 degree at positive z-axis. Angle will be 180 degree at negative z-axis. So phi is from 0 to pi. From 0 degree to 180 degree. At z-axis, angle phi is 0. At negative z-axis, angle phi is 180 degree, which is pi. Then we try to write the function. Try to write this function in terms of rho theta phi. X squared plus y squared plus z squared is always rho squared. That's one of the formula. X squared plus y squared plus z squared is rho squared. And dv is rho squared sine phi d rho, match this order, d rho d phi d theta. Then I can multiply integrand together. Theta from 0 to 2 pi. Phi from 0 to pi. Rho from 2 to 4. Rho to the power of 4. Sine phi. D rho d phi d theta. Here, I can write the integrand as a function of rho, function of phi, function of theta multiplied together. I can write the integrand as a function of rho, function of phi, function of theta multiplied together, and all the limits are constants. So I can split this triple integral into 3 single integrals. Here I can split this triple integral into 3 single integrals. Theta is from 0 to 2 pi. Function of theta is, there's no function of theta, so we assume it's 1. D theta. Phi is from 0 to pi. Phi is from 0 to pi. Function of phi is sine phi. D phi. Rho is from 2 to 4. Function of rho is rho to the power of 4. D rho. Then we can solve each integral, then multiply together. Take antiderivative for 1, we get theta. theta is from 0 to 2 pi. Take antiderivative for sine phi. I have negative cosine phi from 0 to pi. Take antiderivative for rho to the power 4. That's rho to the power 5 over 5 from 2 to 4. For the first integral, if I substitute 2 pi, I get 2 pi. If I substitute 0, I get 0. For the second integral, if I substitute pi, cosine pi is negative 1. Negative 1 is positive 1. If I substitute 0, I get 1. I have 1 minus negative 1. Third integral, if I plug in 4, 4 to the power 5, 4 raised to the power 5 is 1024 over 5. If I substitute 2, 2 raised to the power 5 is 32 over 5. Then we have 2 pi times 1 minus negative 1 is 2. 1024 minus 32 is 992 over 5. Then I use my calculator. I get 3968 over 5 times pi. 3968 over 5 times pi. That's the final answer. Next example. Evaluate the triple integral x squared plus y squared plus 1 over the starting region E, where E is the upper half hemisphere, center and origin with radius 2. Let's draw E first. Try to draw E first. E is the upper half hemisphere. Center and origin with radius 2. Upper half hemisphere. Center and origin with radius 2. This is E. Then let's set an integral. Rho is from 0 to 2. Radius start from 0. It's keep going up. It's keep increasing until 2. Rho is from 0 to 2. Radius is from 0 to 2. It's a full cycle around z-axis. The graph is a full cycle around z-axis. Theta is from 0 to 2 pi. It only includes region above xy plane. It only includes the solid above xy plane. So phi is from 0 to pi over 2. Angle is 0 degree at z-axis. In xy plane, angle is 90 degree. From z-axis to xy plane, the angle is 90 degree. So phi is from 0 to pi over 2. Next, try to write x squared and y squared in terms of rho, theta, and phi. Try to write x and y in terms of rho, theta, and phi. We know x squared plus y squared is r squared. And also we know that r is rho sine phi. R is rho sine phi. So x squared plus y squared is rho squared sine squared phi plus 1. dv is rho squared sine phi. Rho squared sine phi. D rho, match this. D rho, d phi, d theta. Next, simplify the integrand first. Theta from 0 to 2 pi. Phi from 0 to pi over 2. Rho from 0 to 2. Distribute. We have rho to the power 4 sine cube of phi plus rho square sine phi. D rho, d phi, d theta. Solve the inner integral first. take antiderivative for rho first. Theta is from 0 to 2 pi. Phi is from 0 to pi over 2. Take antiderivative with respect to rho. We have rho to the power of phi over phi, which is 1/5 rho to the power of phi, sin to the power of 3 of phi, plus 1/3 rho to the power of 3 sin phi. Rho is from 0 to 2 d phi d theta. If we substitute 0 for each rho, I get 0. So all we need is substitute 2. Theta is from 0 to 2 pi. Theta is phi is from 0 to pi over 2. If I substitute 2 for rho, 2 to the power of phi is 32. I get 32 over phi. Sin to the power of 3 phi plus a over 3 sin phi d phi d theta. Take antiderivative for each of them. How do we take antiderivative for sine cube? For sine cube, if we take antiderivative, this can be rewritten as sine square phi times sin phi d phi. Sine square phi can be rewritten as 1 minus cosine square phi sin phi d phi. Let u be cosine of phi. du will be negative sin phi d phi. If I substitute, I have 1 minus u square sin phi. Here there's an extra negative sign, so sin phi is negative du. If I distribute negative sign, I have u square minus 1 du. Take antiderivative, I get u to the power 3 minus u. U to the power 3 minus u. Then substitute cosine. We have cosine to the power 3 phi over 3 minus cosine phi. Cosine to the power 3 phi over 3 minus cosine phi. So take antiderivative with respect to phi. We have 32 over phi times cosine to the power 3 5 over 3 minus cosine phi. Take antiderivative for sine cube of phi. I get this. Put it here. A over 3 times. Take antiderivative for sine phi. I get negative cosine phi. Evaluate from 0. Phi is from 0 to pi over 2 d theta. Theta is from 0 to 2 pi. If I substitute pi over 2, cosine pi over 2 is 0. So 0, 0, 0, everything is 0. If I substitute 0, 32 over 5 stays the same. Cosine 0 is 1. Cosine 0 is 1. I get 1/3. Cosine 0 is 1. Cosine 0 is 1. Simplify here. 1/3 minus 1 is 2/3. One third minus 1 is negative 2/3. Minus a over 3. d theta. Use my calculator, I get 104 over 15 d theta. Take antiderivative with respect to theta. I have 104 over 15 theta from 0 to 2 pi. If I substitute 0, I get 0. If I substitute 2 pi, I get 208 over 15 pi. 208 over 15 pi. That's the final answer. Next example. Evaluate the triple integral of Sy over E, where E is a solid region in the first octant. Above the cone, S squared plus Y squared equal to Z squared. And below the sphere, S squared plus Y squared plus Z squared equal to 9. In order to set down the integral, let's first of all draw the solid region E first. Let's draw solid region E first. E is a solid region in the first octant. Above the cone, S squared plus Y squared equal to Z squared. Above the cone. Below the sphere, S squared plus Y squared plus Z squared equal to 9. So let's study region E. E is a region in the first octant above the cone and below the sphere. Next, let's set our triple integral based on this sphere. This triple integral over region E can be rewritten as angle theta. Here, theta varies from 0 to pi. Theta varies from 0 to pi over 2 in the first octant. Theta varies from 0 to pi over 2. Angle phi varies from z-axis to the cone. So angle phi varies from the z-axis to the points on the cone. For the points on the z-axis, angle phi is 0. How about what's the phi value for the points on the cone? So let's pick a point on the cone. Distance from the point to the z-axis is r, and the z-coordinate of the point is z. This is angle phi. In this triangle, tangent phi is opposite over adjacent, r over z. And for all points on the cone, we have x squared plus y squared equal to z squared. We know that x squared plus y squared is r squared. And this point is above xy plane, so the z coordinate must be positive. Since r is always positive, z must be positive here. So r equal to z. If I take square root on both sides, r equal to z. Then, since r equal to z, I have tangent phi equal to r over r, which is 1. That means angle phi must be pi over 4 for all points on the cone. For all points on the cone, phi must be pi over 4. So angle phi varies from 0 to pi over 4. How about rho? Rho is the radius of the sphere. Here, radius of the sphere is 9. So rho varies from 0 to 3. Next, we try to write x and y in terms of rho, phi, and theta in spherical coordinates. try to write x and y in terms of rho, phi, and theta. We know that in spherical coordinates, x is rho sine phi cosine theta. Y is rho sine phi sine theta. So I have rho sine phi cosine theta. Y is rho sine phi sine theta times dv. In spherical coordinates, dv is always rho square sine phi, d rho, d phi, d theta. So dv is rho square sine phi rho square times sine phi, d rho, d phi, d theta. Then let me rewrite the integral and make it a little clearer. Theta from 0 to pi over 2. Phi from 0 to pi over 4. Rho is from 0 to 3. Rho times rho square is rho to the power 4. Sine phi times sine phi times sine phi is sine cube of phi. And we have cosine theta, sine theta. D rho, d phi, d theta. D rho, d phi, d theta. Now, in this integral, the integrand can be written as a product of function of rho times function of phi times function of theta. And all limits are constants. So I can split this three-point integral, write it as a product of three single integrals. Here, theta is from 0 to pi over 2. Function of theta is cosine theta, sine theta, d theta. Rho is from 0 to pi over 4. Function of rho is sine cube of rho times d rho. Function of phi is from 0 to pi over 4. Function of phi is sine cube of phi times d phi. Rho is from 0 to 3. Rho is from 0 to 3. Function of rho is rho to the power 4 times d rho. Next, we solve each integral individually, then multiply the answer together. Let me solve the first integral first. For the first integral, I make u substitution. Let u be sine theta. Then du can be written as derivative of sine is cosine. Du is cosine theta, d theta. So sine theta become u. Cosine theta, d theta become du. Now for the upper and lower limit, if I plug in pi over 2 for theta, sine pi over 2 is 1. If I plug in 0 for theta, sine 0 is 0. Then take an antiderivative. With respect to u, I get u squared over 2. And evaluate from 0 to 1. If I plug in 1, I get half. If I plug in 0, I get 0. So the answer to the first integral is half. Next, let's take the second integral. Sine cube of phi can be rewritten as sine square of phi times sine phi d phi. Sine square of phi can be rewritten as 1 minus cosine square of phi sine phi d phi. Here I can make u substitution. Let u be cosine phi. Let u be cosine phi. Then du will be negative sine phi d phi. So this integral can be rewritten as integral 1 minus u squared times negative du. And for the upper and lower limit, if I plug in pi over 4 for phi, cosine pi over 4 is 1 over radical 2. If I plug in 0, cosine of 0 is 1. Since the upper limit is less than lower limit, if I switch the upper and lower limit, I need to switch the sign for this integral. So negative become positive. I get 1 minus u squared du. Then take antiderivative. I get u minus u to the power 3 over 3. Evaluate from 1 over radical 2 to 1. If I plug in 1, I get 1 minus the third. If I plug in 1 over radical 2, I get 1 over radical 2 minus 1 over 2 radical 2 over 3. That can be rewritten as 2 over 3 minus 1 over radical 2 plus 1 over 6 radical 2. Then I use my calculator. 2/3 minus 1 over radical 2 plus 1 over 6 radical 2 is 4 radical 2 minus 5 over 6 radical 2. That's an answer to the second integral. Next, we solve the third integral. Integral from 0 to 3 rho to the power 4 d rho. Let me solve it here. Rho from 0 to 3 rho to the power 4 d rho. If I take antiderivative, I get 1 over 5 rho to the power 5. Evaluate from 0 to 3. If I plug in 3 to the power 5 is 243 times 1 over 5 is 243 over 5. If I plug in 0, I get 0. So the answer to the third integral is 243 over 5. Then the final answer. For the final answer, we multiply the answer to the first integral, the answer to the second integral, and the answer to the third integral together. I get a half times 4 radical 2 minus 5 over 6 radical 2 times 243 over 5. Then multiply together. I get 243 times 4 radical 2 minus 5 over 60 radical 2. After cancellation, I get 81 times 4 radical 2 minus 5 over 20 radical 2. If I rationalize the denominator, if I try to rationalize the denominator, I multiply top and bottom by radical 2. So the final answer is 81 times a minus 2 radical 5 radical 2 over 40. That's the final answer to this 3-point integral. Next, evaluate the 3-point integral of z squared over e, where e is a solid region outside the cone 3x squared plus 3y squared equals z squared, and inside the sphere x squared plus y squared plus z squared equals 16. So in order to set up 3-point integral, let's draw the solid region first. The solid region E is a region outside the cone but inside the sphere. It looks like this. Assume that's a sphere and that's the cone. We are looking for the solid region outside the cone but inside the sphere. That's solid region E. Here is the z-axis. That's the y-axis. That's an x-axis. Next, let's set up treatment integral using spherical coordinates. Since the solid region E is a full cycle around the z-axis, theta varies from 0 to 2 pi. Now, for angle phi, since we are looking for a solid region outside the cone, inside the cylinder, inside the sphere, so angle phi varies from upper half, the surface of the upper half of the cone, to the surface of the lower half of the cone. So angle phi varies from the upper half surface of the cone and then to the lower half surface of the cone. Let's try to find angle phi here. So let's pick a point on the surface. The distance from this point to the z-axis is r. And the z-coordinate of the point is z. This is angle phi. This is angle phi. Then we know that in this right triangle, r is on the opposite side, z is the adjacent side. Tension of angle phi is opposite over adjacent, r over z. Now, since this point lies on the surface of the cone, it must satisfy the cone. For the points on the cone, we have 3x squared plus 3y squared equal to z, which means 3 times x squared plus y squared equal to z squared. It should be z squared here. And we know that x squared plus y squared is r squared. And if I take square root on both sides, z equal to plus or minus square root of 3r. Z could be either positive or negative. For this point here, z is positive. And for this point here, z is negative. Z could be either positive or negative. For the point above xy plane, z is positive. And for the point below xy plane, z is negative. So if I plug in, tension theta can be rewritten as r over plus or minus radical 3 times r. Cancel r. Tension phi is plus or minus 1 over radical 3. Tension phi is plus or minus 1 over radical 3. So let's find the reference angle first. Reference angle of angle phi is pi over 6, because tension pi over 6 is 1 over radical 3. Now, angle phi varies from 0 to 180 degree. Angle phi varies from 0 to 180 degree, which means in the xy plane, it lies in the first and the second quadrant. For angle in the first quadrant, angle phi is the same as the reference angle. That's pi over 6. For the angle in the second quadrant, the actual angle phi is pi minus the reference angle. For the angle in the second quadrant, the actual angle phi is pi minus the reference angle, which is 5 pi over 6. So angle phi varies from pi over 6 to 5 pi over 6. So angle phi here varies from pi over 6 to 5 pi over 6. Now the rho, since the radius of the sphere is 4, this thing is 4 squared. Since the radius of the sphere is 4, rho varies from 0 to 4. And since we are using spherical coordinates, we must convert SYZ to rho, phi, and theta. So here, z squared, z can be rewritten as rho cosine phi. Z can be rewritten as rho cosine phi. So z squared should be rho squared cosine square of phi. So z squared can be rewritten as rho squared times cosine square of phi. then we need to convert dv. In spherical coordinate, dv is always rho square sine phi, d rho, d phi, d theta. In spherical coordinates, dv is always rho square sine phi, d rho, d phi, d theta. So here, dv is rho square sine phi, d rho, d phi, d theta. Next, let me rewrite this integral here. Theta is from 0 to 2 pi. Phi is from pi over 6 to 5 pi over 6. Rho is from 0 to 4. Rho square times rho square is rho to the power of 4. And I have cosine square phi times sine phi. D rho, d phi, d theta. Now here, the integral can be written as a product of function of phi times function of rho times function of theta. And all limits here are constants. So I can rewrite the triple integral as a product of 3 single integrals. Theta is from 0 to 2 pi. Function of theta is 1 times d theta. Rho is from pi over 6 to 5 pi over 6. Function of rho is phi is from pi over 6 to 5 pi over 6. And function of phi is cosine square phi times sine phi d phi. Rho is from 0 to 4. Function of rho is rho to the power 4 times d rho. Then we solve each integral individually and multiply their answer together. If I solve the first integral, I take antiderivative of 1 with respect to theta. I get theta evaluate from 0 to 2 pi, which is 2 pi minus 0. So I get 2 pi. So the answer to the first integral is 2 pi. For the second integral, we can make u substitution here. For the second integral, I can make u substitution. Let u equal to cosine phi. If I take derivative, du is negative sine phi d phi. So cosine square phi can be written as u squared. Sine phi d phi can be written as negative du. Now for the upper and lower limit, we plug in 5 pi over 6 into the function and plug in pi over 6 into the function here. If I plug in 5 pi over 6 for angle phi, cosine 5 pi over 6 is negative. Cosine is negative in quadrant 2. So that's negative radical 3 over 2. If I plug in pi over 6, cosine pi over 6 is positive radical 3 over 2. Here, since the upper limit is less than the lower limit, I need to interchange the upper and lower limit. If I interchange the upper and lower limit, the sign of the integral will be changed. So lower limit become negative radical 3 over 2. Upper limit is radical 3 over 2. And the sign of integral will be changed. Negative become positive. It becomes u squared du. Then take an antiderivative with respect to u. I get 1/3 of u cubed. Evaluate from negative radical 3 over 2 to positive radical 3 over 2. If I plug in radical 3 over 2, I get 1/3 of radical 3 over 2 cubed minus negative minus 1/3 times negative radical 3 over 2 cubed. If I multiply the perfect cube out, I get 3 radical 3 over a. Double negative become positive. 1/3 times 3 radical 3 over a. And here, 3 on the top and the bottom can cancel. we get radical 3 over a plus radical 3 over a, which is radical 3 over 4. That's the answer to the second integral. Then solve the third integral. If I take antiderivative with respect to rho, I get 1/5 rho to the power 5. Evaluate from 0 to 4. If I plug in 4 to the power 5 is 1024. So I get 1024 over 5. If I plug in 0, I get 0. 1024 over 5 minus 0 is 1024 over 5. That's the answer to the third integral. So for the final answer, we multiply all these three numbers together. So for the final answer, take 2 pi times radical 3 over 4 times 1024 over 5. 1024 divided by 4 is 256. If I multiply 1024 divided by 4 is 256. 256 times 2 is 512. So I get 512 radical 3 over 5 times pi. That's the final answer to this 3-point integral. Next example, x from -2 to 2, y from negative radical 4 minus s squared to positive radical 4 minus s squared, z from negative radical 4 minus s squared minus y squared to positive radical 4 minus s squared minus y squared. Integral is 1, dz, dy, dx. If we try to solve this integral directly, there are too many square roots, it's very hard. If we try to solve it directly, there are too many square roots, it's very hard. So let's try to draw the side region and try to set out the integral in a different way. Let's try to draw the side region first, then set out the integral in a different way. See if it could be a little easier or not. See if it could be a little easier. Now, lower bound is z equal to -4 minus s squared minus y squared. If I square both sides, I have z squared equal to 4 minus s squared minus y squared. If I bring s and y over, I have s squared plus y squared plus z squared equal to 4. That's a sphere. This z is negative. This is the lower half hemisphere. And from the top, do the same thing. From the upper limit, do the same thing. Square both sides. Z squared equal to 4 minus s squared minus y squared. If I bring s and y over, I have s squared plus y squared plus z squared equal to 4. This is the upper half hemisphere. Since z is positive, this is the upper half hemisphere. So the graph is an entire sphere. It's one sphere. We take integral from lower sphere to the upper sphere. The graph is a sphere. The top surface is z equal to radical 4 minus s squared minus y squared. This is the upper half hemisphere. Lower surface is z equal to negative radical 4 minus s squared minus y squared. That's the lower half hemisphere. Projection in the xy plane. The projection in the xy plane. This looks like a type 1 solid. Projection, we can consider this as a type 1 solid. Projection in the xy plane is the equator. Projection in the xy plane is this equator, which is a circle. Can we tell the radius of the circle? So to find the radius of the circle, we know that in the xy plane, z coordinate must be 0. In the xy plane, z coordinate must be 0. If I substitute 0 for the z coordinate, I have s squared plus y squared equal to 4, which is a circle of radius 2. Sorry, it should be 4. It should be okay. That's a circle of radius 2. Yes, that's a circle of radius 2. That's a circle of radius 2. So The projection in the xy plane is a circle of radius 2. Next, let's look at y bound. If I square both sides, y squared equal to 4 minus s squared. If I bring s squared over, I have s squared plus y squared equal to 4. That's a circle of radius 2. That's a circle of radius 2. Since y is negative, that's the lower half of the circle with radius 2. That's y equal to negative radical 4 minus s squared. That's the lower half of the circle. For the upper limit, if I square both sides, y squared is 4 minus s squared. If I bring s squared over, s squared plus y squared equal to 4. That's also a circle. Since y is positive, this is the upper half of the circle. This is the upper half of the circle. So upper half is y equal to, upper curve is y equal to 4 minus s squared. We're looking for the region between these two circles, these two semicircles. And x varies from negative 2 to 2. We have the entire circle. So since the region in xy plane, since the projection in xy plane includes in the entire circle, since the projection in the xy plane includes the entire circle, the volume is everything inside this sphere. Since the projection in xy plane is the equator here, the volume is everything between these two surfaces, which means that everything inside the sphere. So since the volume contains everything inside the sphere, if we use spherical coordinate, theta is from 0 to 2 pi. We have everything around the z-axis. Theta is from 0 to 2 pi. Phi is from 0 to pi. It varies. Phi varies from positive z-axis to negative z-axis. It's from 0 to pi. Rho varies from 0 to 2. Because the radius of the sphere is 2, so rho varies from 0 to 2. Number 1 stays the same. dy, dz, dy, dx is dv, and we know dv is rho squared sine phi, d rho, d phi, d theta. Then since all limits are constant, I can write the integral as a function of rho, function of phi times function of theta. So I can rewrite this triple integral as the product of 3 single integrals. Theta is from 0 to 2 pi. Function of theta is 1. Phi is from 0 to pi. Phi is from 0 to pi. Function of phi is sine phi, d phi. Rho is from 0 to 2. Rho squared, d rho. Then let's multiply out. Take an integral for each of them, multiply out. Antiderivative of 1 is theta. Theta varies from 0 to 2 pi. Antiderivative of sine phi is negative cosine phi. Phi varies from 0 to pi. Antiderivative of rho squared is 1/3 of rho cube. Rho varies from 0 to 2. Then evaluate each pi individually. If I substitute 2 pi, I get 2 pi. If I substitute 0, I get 0. So the answer is 2 pi for the first integral. Second integral, if I plug in pi, cosine pi is negative 1. So here, negative 1 is positive 1. If I substitute 0, cosine 0 is 1. I have 1 minus negative 1. If I substitute 2 to the power 3 is 8, I get 8 over 3. If I substitute 0, I get 0. So I have 2 pi times 2 times 8 over 3, which is 2 times 2 is 4, 4 times 8 is 32. 32 over 3 pi. That's the final answer. So if I change the integral, if I change this to spherical integral, it's much easier than we solve it directly. Next, x is from 0 to 1 y is from 0 to radical 1 minus s squared. Z is from radical s squared plus y squared to 1 plus radical 1 minus s squared minus y squared. Integrand is 1. dz, dy, dx. If we try to solve this integral directly, we can see that there are too many square roots. It cannot be very hard. It cannot be a lot of trick substitution. It will be very hard. Can we find an easier way to solve this integral? So let's try to draw the solid region first, then try to set our integral in a different way. Let's try to draw the solid region first, then try to set our integral in a different way. Lower bound, z equal to radical s squared plus y squared. This is a cone. This is a cone. Z equal to radical s squared plus y squared. This is a cone. Upper bound, z equal to 1 plus radical 1 minus s squared minus y squared. What kind of graph it is? Let's simplify first. I can first of all bring 1 over. I can make z minus 1 equal to radical 1 minus s squared minus y squared. Then I can square both sides. z minus 1 squared is radical. z minus 1 squared is 1 minus s squared minus y squared. If I bring s and y over, I have s squared plus y squared plus z minus 1 squared equal to 1. This is a sphere. This is a sphere centered at 0, 0, 1 with radius 1. And since the radical, z minus 1 is positive radical, so this is the upper half hemisphere. This is the upper half hemisphere centered at 0, 0, 1 with radius 1. This is the upper half hemisphere. This is upper half hemisphere. The lower surface is the cone. This is number 1. How do we know they intersect? How do we know this sphere and this cone intersect at 1? How do we know that? How do we know they intersect at 1? So at 1, when z is 1, in the cone, when z is 1, we have, in the cone, when z is 1, we have 1 equal to s squared plus y squared. When z is 1, the cone is a circle of radius 1. When z is 1 in the sphere, we have s squared plus y squared equal to 1. It's also a circle of 1. So when z is 1, they both meet at a circle here. When z equal to 1, they both have the same equation. That means they meet somewhere here. These two surfaces meet at z equal to 1. Now, if we try to use spherical coordinate, one more thing. The projection of this solid in the xy plane is this circle. The projection of this solid in the xy plane is this circle here. The projection in the xy plane is this circle. The projection in the SY plane is this circle. Projection of the solid in the SY plane is this circle. Now let's check the projection in the SY plane. See if we match. Based on the graph, the projection should be the circle of radius 1. Based on the graph, the projection should be a circle of radius 1 in the SY plane. Let's check the actual projection, see if they match or not. Let's check their actual projection, see if they match or not. For the y bound, lower bound is y equal to 0. Y equal to 0 is s-axis. Y equal to 0 is the s-axis. Upper bound is y equal to 1 minus radical x. Radical 1 minus s squared. Upper bound is radical 1 minus s squared. If I square both sides, y squared is 1 minus s squared. If I bring s squared over, I have s squared plus y squared equal to 1. That's a circle of radius 1, which is upper, since y is positive, that's an upper half. That's an upper half semicircle. So we are looking for region between y equal to 0 and the upper half semicircle. X is from 0 to 1. So we only have this region here. That's a quarter of a circle. That's a quarter of a circle. So the projection is only this part. If the projection in the SY plane is only this part, we don't have the entire ice cream cone. We don't have the entire ice cream cone here. So let me draw the picture over. We don't have the entire ice cream cone. We only have a quarter of the cone. We only have a quarter of the ice cream cone. Let me draw the picture over. We only have a quarter of an ice cream cone. We only have a quarter of ice cream cone. So here, it's not a full cycle. It's not a full cycle around the z-axis. Theta actually varies from 0 to pi over 2. Theta varies from 0 to pi over 2. It's not a full cycle. How about phi? This graph touches z-axis, so phi actually starts from 0. But angle phi terminates at the surface of the cone. Angle phi varies from z-axis to the surface of the cone. Angle phi varies from z-axis to the surface of the cone. At the z-axis, angle phi is 0. At the z-axis, angle phi is 0. What's the angle phi at the surface of the cone? Let's pick one point here. Pick one point on the surface of the cone. Then from the distance from the point to z-axis is r. And this distance here is z. This distance here is z. Angle phi is the angle between z-axis and the surface of the cone. This is angle phi. We know that tension phi is opposite over adjacent, r over z. And since this point located on the cone, this point satisfies the cone. This point satisfies the cone. The cone is z equal to radical s squared plus y squared. So radical s squared plus y squared is s squared plus y squared is r squared. When we take square root, we get r. So actually z equal to r. Z is above SY plane, so Z is positive R. Z equal to R. Since Z equal to R, tension phi must be 1. Then angle phi and the cone must be pi over 4. Angle phi and the cone is pi over 4. So angle phi varies from 0 to pi over 4. Angle phi varies from 0 to pi over 4. How about rho? The vertex of the cone touch the origin, so actually rho starts from 0. The upper bound of this solid is this hemisphere here. Upper bound of this ice cream cone. The upper bound of this ice cream cone is the hemisphere here. So we try to get rho from this sphere. So try to get rho from this sphere. Upper bound of this ice cream cone is the sphere here. So try to get rho from this sphere. This sphere here we have s squared plus y squared plus z squared minus 1. S squared plus y squared plus z squared minus 1 plus z minus 1 squared equal to 1. If I expand the perfect square, I have s squared plus y squared plus z squared minus 2z plus 1 equal to 1. I can cancel 1 from both sides. So s squared plus y squared plus z squared, cancel 1 from both sides. Move 2z over, move negative 2z over, become positive 2z. S squared plus y squared plus z squared is rho squared. Z is rho cosine phi. Z is rho cosine phi. I can cancel one rho from both sides. Rho equal to 2 cosine phi. Rho equal to 2 cosine phi. So that's an upper bound. I write this hemisphere in terms of rho. I write this hemisphere as a function of rho. So that's a spherical equation for this hemisphere. That's a spherical equation for this hemisphere. So this hemisphere can be represented by rho equal to 2 cosine phi. So the hemisphere can be represented by rho equal to 2 cosine phi. So, and the vertex of the cone touch the origin. Rho starts from 0, gets larger until we touch this hemisphere, which is rho equal to 2 cosine phi. And number 1 stays the same. dz dy dx is the same as dv. And for spherical coordinate, dv is rho square sine phi d rho d phi d theta. Then solve the integral first. Solve the integral first. Take antiderivative with respect to rho. I have rho to the power 3 over 3, which is 1/3 of rho cube. Sine phi. Rho is from 0 to 2 cosine phi d phi d theta. Substitute 2 rho phi. We have 1/3 of 2 rho phi cube. 2 times 2 cube is 8. Cosine cube phi times sine phi. If I plug in 0, I get 0. d phi d theta. Then this is a function of phi, and the limits are constants. I can write this as 2 single integrals, then multiply out. Theta is from 0 to 2 pi. Function of theta is 1, d theta. Function of phi is from 0 to pi over 4. 8 over 3 cosine cube phi times sine phi d phi. First integral, if I take antiderivative, I get theta from 0 to pi over 2. If I plug in pi over 2, I get pi over 2. That's the first integral. If I solve the second integral, I make u substitution. The u equal to cosine phi. Du is negative sine phi d phi. So I have a over 3 integral a over 3 u to the power 3 negative du. If I plug in pi over 4, cosine pi over 4 is radical 2 over 2. If I substitute 0, cosine 0 is 1. Then take antiderivative. We have a over 3. If I take antiderivative, if I take antiderivative, I have a over 3 times 1 over 4 u to the power 4, and it's negative. Evaluate from 1 to radical 2 over 2. Radical 2 over 2 is the same as 1 over radical 2. Radical 2 over 2 is the same as 1 over radical 2. Then a over 3 and 1 over 4 can be reduced as negative 2 over 3. If I plug in 1 over radical 2, I have 1 over 4. If I substitute 1, I have 1. So here I have negative 2 over 3 times negative 3 over 4. Cancel 3, cancel 3. I have 2 over 4. 2 over 4 is 1/2. So the final answer, pi over 2 times 1/2. The final answer is pi over 4. The final answer is pi over 4. So, using spherical coordinate, we can solve the integral a little easily, better than solving these 2 square roots. Next, find the volume of a sphere with radius 4. So to make the graph a little easier, we will draw a sphere, center and origin with radius 4. To make the graph a little easier, to make calculation a little easier, I will draw a sphere, center and origin with radius 4. I'll draw sphere, center and origin with radius 4. Then we are looking for the volume of the entire sphere. For volume of a solid region is always the triple integral of 1 over the solid region E. That's the volume formula. So when we set down triple integral, use this formula. We have entire cycle around the z-axis. So theta is from 0 to 2 pi. We have everything from positive z-axis to negative z-axis. So rho varies from 0 to pi. Angle phi varies from 0 to pi. Angle phi varies from 0 to pi. We have everything from positive z-axis to negative z-axis. So angle phi varies from 0 to pi. And radius of the sphere is 4. That means rho varies from 0 to 4. It starts from 0, gets larger, 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 eventually reach 4. Rho varies from 0 to 4. Number 1 stays the same. dV is rho square sine phi. d rho d phi d theta, d rho d phi d theta. Which is here, if you observe this integral, all limits are constants, and I can write the integral as a product of function of rho times function of phi times function of theta. So I can separate this triple integral into 3 single integrals and solve each one individually. Theta is from 0 to 2 pi. Function of theta is 1 d theta. Phi is from 0 to pi. Function of phi is sine phi d phi. Rho is from 0 to 4. Function of rho is rho squared d rho. Then solve each single integral and multiply out. We have theta from 0 to 2 pi. Next one is negative cosine phi. Phi varies from 0 to pi. Last one is rho cube over 3. Rho varies from 0 to 4. Solve each one individually. First one is 2 pi. Second one is 1 minus negative 1. The third one is, if I plug in 4, that's 64 over 3. If I plug in 0, I get 0. 2 pi times 2 times 64 over 3, which is 2 times 2 is 4. 4 times 64 is 256 over 3 pi. Can we check the answer? In high school, we know that volume of a sphere is 4 over 3 pi r cubed. That's a formula we know from high school. Volume of a sphere is 4 over 3 pi r cubed. R is 4. If I substitute 4 here, 4 to the power 3 is 64. 64 times 4 is 256. We get the same answer. We get exactly the same answer. Next, find the volume of a cone whose base radius is phi and the height is a. Find the volume of a cone whose base radius is phi and height is 8. This same thing. Volume of a side region is a triple integral of 1 over the side region E. Let's draw the side region first. Let's draw the cone first. In order to make the integral a little easier, we try to draw the vertex of the cone on the origin. In order to make the calculation easier, we try to draw the vertex of the cone in the origin. That's a cone. We're looking for the volume of a cone, which means volume below this plane. The height of the volume is a. So we're looking for the volume of the cone below the plane z equal to a. We're looking for the volume inside the cone below the plane z equal to a. And the radius is 5. This side is a, this side is 5. How do we find the volume of the cone? So this is a full cycle around z-axis. So if we set up an integral, we can tell that theta is from 0 to 2 pi. Here we have a full cycle around z-axis. Theta is from 0 to 2 pi. How about angle phi? Angle phi starts from positive z-axis. So angle phi actually starts from 0. What's this side here? Angle phi varies from this side to the edge of the surface, to the edge of the cone. Angle phi varies from z-axis to the surface of the cone. Angle phi varies from z-axis to the surface of the cone. What's phi here? Here, tension phi. Tension phi is opposite over adjacent phi over a. So phi is inverse tension of phi over a. This is not a special value. We leave it the way it is. How about rho? Vertex of the cone is on the origin, so rho starts from 0. Rho keep going up, keep going out, and it's bounded by the plane g equal to a. Rho is bounded by the plane g equal to a. How do we find a spherical equation for g equal to a? How can we find a spherical equation for g equal to a? G equal to a. Let's try to find a spherical equation for g equal to a. We know that g is always g equal to rho cosine phi. If I try to isolate rho, I divide both sides by cosine phi. So rho equal to a over cosine phi. It can be rewritten as a secant phi. So that's the upper bound. Lower bound is 0. Upper bound is rho equal to a secant phi. Then number 1 stays the same. dv is rho square sine phi. dv is rho square sine phi. d rho d phi d theta. Let's take antiderivative for rho first. Let's take antiderivative with respect to rho first. We have 1 over 3 rho cube sine phi evaluate from 0 to a secant phi d phi d theta. Solve this integral. Substitute the upper limit for rho. Substitute the upper limit for rho. A to the power 3 is phi 12. I get phi 12 over 3 secant cube. Secant cube of phi times sine phi d phi d theta. Then here I can separate it. Theta is from 0 to 2 pi. They both have constant, they all have constant limits here. 0 is constant, 2 pi is constant, 0 is constant. Inverse tension of phi over 8. This is also constant, and I can write the integral as a function of rho times function of phi. So function of theta times function of phi. Function of theta is 1 d theta. Phi is from 0 to inverse tension 5 over a. Phi 12 over 3 secant cube phi times sine phi. Secant cube phi, I can try to write it as 1 over cosine cube phi. That's a little easier. When we see sine, try to write secant in terms of cosine. Next, first one is easier. Theta from 0 to 2 pi, which is 2 pi. Second one here, let's try a U substitution. Let U be cosine of phi. Let U be cosine of phi. Du will be negative sine phi d phi. So this integral can be rewritten as phi 12 over 3 1 over u to the power 3 times negative du. Now how do we change the limit here? How do we change the limit? If we plug in 0, cosine 0 is 1. If I plug in this crazy number, what do we get? If we plug in this crazy number, what do we get? If we plug in this crazy number, we have cosine of inverse tension of phi over a. What do we get here? How do we evaluate this? Remember, this represents angle value. Inverse tension of phi over a. This represents angle value. Inverse tension of phi over a equal to phi. That means this can be rewritten as cosine phi. We know that tension phi is phi over a. What's cosine phi? Tension phi is phi over a. What's cosine phi? Based on tension phi, let's draw a triangle. Tension means tension is opposite over adjacent. Use Pythagorean theorem, we can find the missing side here. Use Pythagorean theorem, we can find the missing side. A squared plus phi squared. A squared is 64. Phi squared is 25. Together is 89. That's radical 89. Then cosine of angle phi. Cosine of angle phi. Cosine function is adjacent over hypotenuse. A over radical 89. So the upper limit is A over radical 89. Then simplify this integral. I can pull out negative phi 12 over 3. Integral from 1 to a over radical 89. 1 over u to the power 3 can be rewritten as u raised to negative 3 du. Then we take an antiderivative. That's u raised to negative 2 over negative 2. Evaluate from 1 to a over radical 89. Cancel negative 2 with negative phi 12. We have 256 over 3. Now I plug in a over radical 89. It becomes 89 over 64. If I plug in 1, I get 1. Multiply, I have 25 over 64. If I subtract, I have 25 over 64. 256 divided by 64 is 4. So I get 100 over 3. That's the integral of the second. That's the answer of the second integral. Then multiply 2 pi times 100 over 3. The final answer 2 pi times 100 over 3 is 200 over 3 pi. Let's check the answer. We know that volume of a cone is 1/3 of pi r squared h. Volume of a cone is 1/3 of pi r squared h. For this cone, base radius is 5, pi is 8. So phi squared times a. Phi squared is 25. 25 times a is 200, which is 200 over 3 pi. We get exactly the same answer. But this way doesn't look too easy. Is there a better way to find the volume of the cone? This way it doesn't look too simple. Is there a better way to find the volume of a cone? Let's try to use cylindrical coordinate, see if it's better or not. Let's try to use cylindrical coordinate. Let's try to use cylindrical coordinate, see if it's better or not. The upper bound is z equal to a, since the height of the radius is a. Upper bound here, upper cover is z equal to a. Lower surface is the cone. Here we need to find the equation for the cone first. This side is phi, this side is a. How do we find the equation for this cone? How do we find the equation for this cone? This is g, this is r. Inside the cone, the ratio is the same everywhere. Inside the cone, the ratio is the same everywhere. So ratio between g and r is a over phi. Inside the cone, ratio of g and r is the same everywhere. They are similar triangles. So g over r is always a over phi. If I solve the equation for g, cross multiply phi g equal to ar. So g equal to a over phi r. This represents the equation of its cone. And we know that r squared is x squared plus y squared. So r is radical x squared plus radical y squared. G can be rewritten as a over phi radical x squared plus y squared. This is the equation of this cone. So that's the lower surface. G equal to a over phi radical x squared plus y squared. That's the lower surface. That's an upper surface. Projection in the xy plane is a circle. Projection in the xy plane is this circle. From top to bottom, all we can see is this circle here. That's the projection in the xy plane. And what's the radius of the circle? This circle has the same size as this circle here. This circle here has radius phi. So the projection in the xy plane also have a radius phi. It's also a circle with radius phi. So projection in the xy plane is a circle of radius phi. That's the projection D in the xy plane. And when we see a circular region, we try to use polar coordinates for S and Y, for S and Y axis. So let's set up the 3-pointer goal here. Upper surface is g equal to a. Lower surface is g equal to a over phi radical x squared plus y squared. Integral is 1 dz. Then take outer double integral over region D dA. Then for region D, since it's a circular region, we try to use polar coordinates in the xy plane. So here r is from, that's a circle of radius 5. So r is from 0 to 5. It's a full cycle. Theta is from 0 to 2 pi. R is from 0 to 5. Then write x and y in terms of r and theta. X squared plus y squared is r squared. Radical r squared is r. The lower bound is a over phi r. Upper bound is a. Integral is 1. dz stays the same. For polar coordinate, dA become r dr d theta. Then we can bring r inside. Make it easier, we can bring r inside. Theta is from 0 to 2 pi. R is from 0 to phi. Bring r inside. Z is from a over phi r to a. Bring r inside, we get r dz dr d theta. Take antiderivative with respect to z. We have rz. Evaluate z from a over phi r to a. dr d theta. Theta from 0 to 2 pi. R from 0 to phi. If I plug in a for r, I get ar. If I plug in a over phi r, if I plug in a for z, I get ar. If I plug in a over phi r for z, I get a over phi r squared dr d theta. Now here we see that all limits are constant. This is a function of r. So I can separate this double integral into two single integrals. Theta is from 0 to 2 pi. Function of theta is 1 d theta. R is from 0 to phi. Function of r is ar minus a over phi r squared dr. Take first integral. We have theta from 0 to 2 pi, which is 2 pi. Take the second integral. I take antiderivative here. I have 4r squared minus a over phi r cubed over 3, which means times 3 on the bottom. I got 15. Evaluate from 0 to phi. If I substitute phi here, phi squared is 25. 25 times 4 is 100. If I substitute phi here, phi to the power 3 is 125. Divide both of them by phi, I get 3 on the bottom. 25 times a is 200. 100 minus 200 over 3. Common denominator is 3. Put it over 1. Multiply top and the bottom by 3. 300 minus 200 is 100. I get 100 over 3 here. That's the integral. That's the answer of the second integral. Then multiply. 2 pi times 100 over 3 is 200 over 3 pi. We get the same answer. So for this problem, if we use cylindrical coordinate, it's a little easier than spherical coordinate. For this problem, if we use cylindrical coordinate, it's a little easier than spherical coordinate.